Hello. So today I want to talk about an informal definition of limits, graphically, numerically, how you can think of this idea of a limit. In particular, we have really three informal definitions: right-handed limit, a left-handed limit, and a two-sided limit. The setup here, we have a function f of x, and you have a is some real number. Typically, a you're thinking of as on the x-axis, right? It's some x value. And so we're going to imagine this function, right? Imagine this graph that you have. And we want to say, as x approaches a from the left, so you have some x value a, and then you're going to pick x values that are smaller than a, but not much. They pick some x value, pick some new x value, pick some new x value, right? So let x approach a from the left. And as you pick these x values, see what the corresponding y values are, right? The corresponding f of x values. So whatever those f of x values are approaching as x approaches a, that value is what we call L, right? So L is that y value that is approached by the y values as x approaches a from the left. Here, you can do the same thing, but from the right. So you could have, again, some function, y equals f of x, right? Which is some random graph, although I guess my two random graphs are sort of the same, not so random, and some not so random value a, which then we have x approaching a from the right. So you could have x now going to a this way, and you can imagine picking different x values, x value, x value, x value, x value, and then you track what the y values are as x approaches a, and you see what that y value is that's being approached. And again, we can call that L. Right, L is the y value that's being approached as x approaches a from the right. Notice this notation, the minus and the plus, right? There's this minus in the left-handed definition. You can think of that as x represents a minus a little, right? 0.1 less than a or something would be the kind of x value that we're talking about here. And similarly for a right-handed limit, it's like x is a plus a little, right? Plus some infinitesimal amount. Is a good way to think of this. A plus 0.1, a plus 0.01, something like that, right? So this is the idea of the left-handed limit and the right-handed limit. Now, if the graph is really well behaved, you'll have that the left and right-hand limits are the same. That it doesn't matter whether you approach a from the left or from the right, you'll converge on the same y value. And if that's the case, then we say the two-sided limit, or notice I have this in parentheses, because sometimes we just say the limit. If you just say the limit and you don't say left hand or right hand, you mean the two-sided limit. So the two-sided limit is when the left and right hand limits are both equal to the same number L, right? That's the two-sided limit. So, and L, I should mention, so one little note is that L can be a number, right? L could be a constant. It could be infinity or it could be minus infinity, right? So L, we're not, A here, we're really taking to mean just a numerical quantity, a real number, fixed, finite, real number. But L could represent plus or minus infinity or a numerical constant. Any of those are valid. So let's look at an example of this. Actually, one more thing I want to say. One more note is the symbol D and E. You'll see that a lot in the context of limits. If the left and right hand limits do not exist or disagree, right? If they disagree, then we say that the two-sided limit does not exist. Right, so the limit as x approaches a would be D and E. So here is a kind of classic example of this framework. Consider the function f of x equals 1 over x squared. Right. So if we have the function 1 over x squared, let's think about what that would look like graphically. by plotting a few points. Well, we're going to actually sort of construct the graph and analyze some limits all in one breath here. So imagine if you have a really, really large magnitude, but negative x value, something like -10, right? Then f of x here is going to be 1 over 100, but it's positive because we squared it, right? -10 squared is positive 100. So this would be 0.01. So down here, I'd have the point at -10. I'd have a point very close to the x-axis, right? -10, comma 0.01. Negative x value, positive y value. And then you can imagine a point like, say, -1, right? So that would be a point, something like this. It would be a point -1, comma +1, because I'd have 1 over -1 squared, which is positive 1. And then you could imagine if we picked a point, say we picked -0.1, that suddenly is going to become very large, right? Because I have 1 divided by -0.1 squared. So this is actually 0.01. And the reciprocal of 1/100th is actually 100, right? So this is going to be not to scale, right? This is going to be way, way, way up high, right? Something up here. This is going to be -0.1, comma +100, right? So this graph is going to look like this. And as I choose x values that are even closer to 0 from the left, right, you're going to get even more gargantuan y values, right? So here I would have, if I square -0.01, one more zero than I intended there. If you square that, right, we have 2 decimal places, but we're squaring it. So now we have 4 places past the decimal. And that then is going to be, its reciprocal will then be 4 zeros, right? After it'll be 10,000, right? It's 1 over a 10,000th. So the reciprocal is 10,000. So you can see here as x approaches 0 from the left, see I'm going -10, -1, -0.1, -0.01, right? X keeps getting closer to 0 from the left. What behavior are we seeing? What's the y coordinate doing? The y coordinate is going to positive infinity, right? So that's the behavior that I observed right here, right? I would say as x approaches 0 from the left, the f of x, which represents the y coordinate, seems to be approaching infinity, right? That's what we're seeing, that it becomes larger and larger and larger. Now, this is writing out that whole phrase is kind of a mouthful. So that's why we have this nice concise notation that we defined up above. The limit of f of x as x approaches 0 from the left equals infinity. Right? It means exactly the same thing. These symbols mean the same thing as that phrase that I just wrote. So there's a left-handed limit. I didn't prove anything formally. I just plugged in some points on the graph and kind of visually looked at, and numerically looked at where the graph is going. Now, let's also think about from the right. Say x is 10, say x is 1, say x is 0.1, say x is 0.01, right? Let's think about these values. Well, I'm squaring everything, so whether it was negative, x was negative or positive, doesn't matter. I actually get the same values, right? This graph is symmetric. This function, in fact, is an even function. It has even symmetry, right? A reflection across the y-axis. So here I get the same values, right? This will be 10,000, 100, 1, 0.01, and I could graph those values too. Right? And if I graph the function, it will look like this. So I could think about this point here, 10, comma 0.01, or this point here, 1, comma 1, or this point here, 0.1, comma 100, or super let's see. Or, and again, super not to scale, right? It should be 100 units up. I'm drawing it by this scale, something at height 4 or something, right? But it represents a point that's way up there. So this is, you can see that as I'm picking these x values, right? As these x values approach 0 from the right, the y coordinate also goes to infinity, just as it did from the left, right? So how would I describe that? Again, I could describe it in words, right? As x approaches 0 from the right, I can also say, once again, f of x approaches infinity. And if I want to write it in our symbols instead of words, I could again say that the limit as x approaches 0 from the right of f of x is infinity. So translating words to symbols, I have a very similar result as before. Now, look at this. The left and right hand limits matched. They're both positive infinity. The L in this case would be positive infinity. So then I could further say, because the left and right hand limits were equal, both infinity, right? Because those match. Maybe match is a better word than equal here, right? Sometimes we get nervous about saying things like infinity equals infinity. That is the relation equals really defined on infinity, or is it strictly for quantities, right? So maybe match, which is a little more casual of a word, is a better thing to say. But since the left and right hand limits match, since they agree, however you want to say it, right? We can say that the limit, the two-sided limit, is able to be written right? You could write it without the plus or the minus, just the limit is infinity. So this is an example of a left-handed limit, a right-handed limit, and then a two-sided limit on the function 1 over x squared. So this is just a bit about how you can plug in some values, make a data table, and analyze some limits. All right, great. Thank you. Hope that was helpful. And we'll talk soon about deltas and epsilons, the way to make all of this formal, thanks to the Greek alphabet. See you soon.